Okay, so we're back. So this is the continuation of our topic of stoichiometry, and just adding a few extra little tidbits of information to what we're already doing. As far as the type of math that we're doing, it's the same, pretty much exactly the same. Only we need to add sort of definitions to understand when to use certain numbers, when to use them at different moments in time. And so this is our topic of limiting reactants and other sort of applications of stoichiometry. So this is our warm-up. So perhaps during our pause, we've looked at this. Let's do it together just to make sure we have an example worked out in the video. What is the maximum amount of lithium fluoride in grams that we can produce from 10 grams of lithium and excess fluorine? Oh, okay. Well, I'm going to have to fix that link later. So we're doing this. Oh, I see. Refresh. Okay, refresh it now, and I think the link will work. Okay, refresh the page, and I think the link to the notes is there. So we write our, again, I like to be sort of super organized with these kinds of problems. We're going to, and it's kind of like the strategy has a formula to it. We're going to write our givens. We're going to write our desired. And our central theme for all stoichiometry problems is moles given to moles desired. The goal is the mole. We want to use a mole recipe. So I'm going to go ahead and write the givens. I was given that there are 10 grams of lithium, and I would like to know the amount of lithium fluoride. So that's how I'm going to organize. And oftentimes the easier thing to do is to identify the desired. What is it that you desire? It's the question part of the problem. What goes with lithium fluoride? So sometimes it's easier to go backwards and identify the desired first. So it's going to be grams of lithium fluoride. So therefore, by process of elimination, the given is going to be 10.0 grams of Li. And since there's excess F2, we don't have to worry about it. But now that I've written my given and desired, I now know what chemical to label as the given. So I'm going to relabel my central theme with that as well. The given is lithium. The desired is lithium fluoride. And so now my strategy is to take my given information and get to my central strategy, get to my center theme. And then get to the end. So now that's going to be my goal. Can I think of a way to do this? Starting with, and again, I always start with, here we go, 10.0 grams of lithium, and there's going to be a necessary conversion. The conversion I need requires me to take grams to moles. Can I think of something that can do that for me? A number that can take grams of something to its moles of something. It's the molar mass again. So again, I'm going to look at the periodic table, use that number as is. There is no changes. There are no changes to that number. So what does it read? It reads 6.94 grams of lithium is a mole of lithium. That's going to give us grams of lithium cancels. That would be, we've made the first hurdle. Now I need to go from moles of given to moles desired. How do I do that every single time? This central strategy is always the same. Moles given to moles of desired using my recipe. So that means using the numbers in my balanced chemical equation. What are those numbers? 2 lithium to 2 fluorine. So that means 2 moles of lithium to 2 moles. Oh, I'm sorry, LiF. LiF, there we go. Yes, you could reduce it, but I say, why do that when you could just copy them down exactly and know that you're using the right numbers? Sometimes if we try to reduce them before plugging them in, we make a mistake. But since the ratio is 2 to 2, yes, that's the same as a 1 to 1. That's fine. But I say if we're going to do this sort of formulaically and practice sort of the strategy with taking as few sort of assumptions or maybe sort of skip steps, I just put the 2's and the 2's in. Yes, we could cancel it, but that's okay. We don't have to. It'll come out the same. That will get us past this arrow. Now it's moles to grams of desired. How am I going to do that? Well, this time I'm going to add up the atoms on the periodic table to get my answer. So that's going to be, again, the unit is grams per mole. So a mole of LiF is going to be, and I already did it on here, 25.94 grams of LiF. So that's going to cancel with that. Oh, I forgot to cancel these. Okay. So that would be my math. There. 10 divided by 6.94, enter. Now you could do times 2 and then divide 2 just to be safe. Times 25.94. That comes out to 37.4 grams of LiF. And that's because this number had 3 sig figs. Our molar masses had 3 sig figs, 4 sig figs. So we go with 3. So this is our conversion, grams of lithium to, this is how much lithium fluoride I should make. Now, if I were to use a term that has the word yield in it, what would I label this as?
Theoretical?
Yeah, this is my theoretical yield. This is what I expect to make from all of my lithium. So if this were a problem that involved a % yield, what we're doing right now is calculating the theoretical yield. So if I react 10 grams of lithium, I should make 37.4 grams of LiF. So it's fairly straightforward, but this kind of question isn't really necessarily what happens every single time in the real world, because there are some times where we won't have plenty of our other ingredients. And that's what we've been assuming. We have always, and sometimes implicitly, assumed that we have plenty of everything else. So we've only been focusing on one ingredient, one reactant. But what happens if I have limited amounts of both? So I have specific amounts of everything. Well, then it becomes a little bit more complicated, but not by much, how we get to the answer. So again, we can think of it like the bike analogy, where instead of having plenty of bike frames, I actually have a limited amount. So I have 4 bike frames and I have 4 wheels. Now my question is, how many can I make with limited quantities of each of them? So in this example, we can kind of sort of visually see it. A reminder that the recipe was that 1 frame and 2 wheels make bike. So with the amount of frames I have, I could potentially make 4 bikes. So in an axis of number of bikes made, so a number line, I could go all the way to, I can make 4 bikes with the amount of wheels that I have. But we know that there are only enough wheels to make 2 bikes. So we would say, well, which is our answer? Well, we only have enough of both ingredients to make 2 bikes. So we are limited to 2 bikes because even though we had enough frames to make 4, we only had enough wheels to make 2. So one of these ingredients is the one that limits us to a smaller amount of product. In this case, in this sort of visual example, my wheels, because they're in technically shorter supply because of the recipe, we would say that this is going to be our, here it comes, limiting reactant. So when we have limited amounts of the reactants or the ingredients, the limiting reactant is the reactant in shortest supply that stops the reaction once it is completely used up. One thing to note is that the limiting reactant does not always the smallest, I'll say given. And then I'll say see last slide for that. Because we actually had equal numbers of each of these. So sometimes there's this sort of trick our brains play on us that like, oh, if I have equal amounts of reactant, then that means they'll both be completely used up. We have to take into account the starting amounts that were given, but also the recipe involved. So there are times where we'll be given, I have this much of this and this much of that, and our brains would want to go to, well, oh, the one that I have less of must be the one that limits me. It gets used up. But that's not always the case because we don't just take into account how much we start with. We take into account how much the recipe calls for as well. And so we'll see that there's sort of a formulaic way to figure out which is my limiting reactant, which one gets used up. And so that's going to require sort of a conversion to allow us to do that. Oh, how do we know which one is the limiting reactant? Whoops. So let's take a chemistry example to see how we do that without the bikes, without the wheels, without the frames, whatever. Let's do one just with moles of a reactant and a chemical equation. So what is the maximum amount of water that can be produced from 12 moles of hydrogen and 7 moles of oxygen? And here's our balanced chemical equation. What we're going to do is we're going to theoretically figure out how much each reactant can produce in the same way that we looked at the frames and we said, this many frames makes this much. This many wheels makes this much. And then we made a decision. We're going to do the exact same thing. So what we do is the calculation twice. I use my balanced chemical equation to tell me how much water am I going to make if I use up all of my hydrogen. So that's what you're seeing here. I'm taking the amount of hydrogen I'm given in moles, and then I'm using the recipe. For every 2 moles of hydrogen, I make 2 moles of water. Then I do the same thing with my oxygen. I start with the amount I was given. And then I say, well, the recipe calls for 1 mole of oxygen makes 2 moles of water. And so I get 2 answers. The amount of hydrogen I have can make 12 moles of water. The amount of oxygen I have can make 14 moles of water. So to see it visually on the number line, we can have a number line with the amount of water that I make, and we can see the difference between our 2 answers, much like we saw it with the bicycle. The amount of water that hydrogen produces is 12. It reaches all the way to 12 on the number line, whereas water reaches 14 on the number line. Much like the bicycle analogy, where we only have enough wheels to make a limited number of bikes, in the same way, we only have enough of both ingredients to produce the smaller amount of water. So we would say, whoops. We would say, this is how much water I expect to make. And I just want to emphasize, what did we do here? We did both calculations to try to see the answer. One temptation is, what do we do with this number? This number is we ignore. So this is because if I had all this quantity of oxygen and I completely reacted it, I would make this much water. But we don't have enough of both ingredients to do that. And we see it on the number line. I have enough of each to make all the way up to 12. But once I go beyond 12, now I don't have enough hydrogen to mix. So we always go with the smaller value. We ignore the other answer. In fact, I'm going to go like, don't even look at it. It was for the purposes of making our decision, but not an answer that we write down as our final answer. For showing work, yes. So again, to apply the terminology, we would say hydrogen is our limiting reactant. And I use, throughout this lecture, I use LR to abbreviate limiting reactant. What that means is that that's the one that stops the reaction from going any further. It gets used up, much like the wheels got used up. It is always the smaller of our 2 possible answers, or it is how we identify it. I should mention that that's the limiting reactant. The other reactant is called the excess reactant. So that's what we were using before. So that's our excess reactant. It means we had extra of it. We had plenty of it. So the idea for a limiting reactant calculation is one in which, and I'll go ahead and emphasize it one more time, have given quantities of more than one reactant. So this is what we do when we have given quantities of more than one reactant. It's not just how much do I make from this one guy. It's we have this much of A, this much of B. What are we going to make? So we have given quantities of more than one reactant. The idea is going to be we assume each reactant completely reacts. So it means that it's just the same math as last lecture, but times 2, meaning we have to just do the same procedure twice to produce a desired product. Then, like the bike analogy, The limiting reactant produces less product because it runs out. We consume it completely. So then we're going to choose the smallest answer, and that is how much we will make. We are limited by the limiting reactant. Much like, and go back to the bike analogy, or if you like a different, recipe, cupcake analogy, we ran out of sugar, right? Something like that. As far as the generic reaction goes, it's, reactant number 1 and reactant number 2 make product number 1 and product number 2. To find the limiting reactant, we're just going to do the same flow chart, but twice. We're going to start with the givens for one of the reactants, and then go through the math to turn it into an amount of product. In this case, product number 1. Then we're going to compare it to how much product we make with the other reactant. So that means take the givens for reactant number 2 and do the same math as in last lecture to get it to product number 1. We have to compare the same thing. And that's how we do this. We choose the one that gives us less product. And that's because smaller answer indicates which R for reactant runs out first. So the limiting reactant question is a little bit more intimidating than it really is, because it's actually the same math as the last lecture, except you do the math twice. And that's basically it, as far as how much should I make. And so just to reiterate, notice that I said P1 and P1. It's because when we're trying to compare, we have to compare apples to apples. So how much of product 1 do I make? How much of product 1 do I make with reactant 1? How much product 1 do I make with reactant 2? We have to compare apples to apples to indicate the right answer. I should mention that there's no reason why we couldn't have done it with the second product. You just have to pick one. But when you pick one, stick with it for the whole thing. But then that's how we do it. So I think we can try it with, can try it with an example. So this is basically the question from before, except we're going to keep adding to it. So now the question is like our warm-up. What is the maximum amount of lithium fluoride in grams that we can produce from 10 grams of lithium? And now I'm going to change it to 10 grams of fluorine. So this becomes a limiting reactant question because we have limited amounts of both of them. That means we're going to do the math for both of them, and then we're going to make a decision. So actually from the warm-up, we've already done this. So this is 10 grams of lithium will make 37.4 grams of product. So again, this was exactly the math, the process from the warm-up. Only for this type of question where it says I have this much A, this much B, now we're going to do it again, take 2, right? 10 grams of fluorine makes how much lithium? And so we're going to do the exact same strategy as before. So just to write the flow chart one more time, again, the center is moles of given to moles desired. And since we're trying to compare our answers, the desired, it should be the same unit as before. So grams of desired is going to be that. Since we're trying to practice with now fluorine, it's going to be grams of F2. And then I'll go ahead and replace the rest of it. So this is going to be F2 because that's our given. We desire the LIF one more time. And so this is our flow chart again. The nice thing is if you can do it once, you can basically use your first set of answers to guide you how to do the second. So I'm going to take the grams and I'm going to use another molar mass. I'm going to use the ratios and then another molar mass. 10.0 grams of F2. And now my goal is the mole. So how do I turn grams into moles? By now you should be sick of me saying that so many times. That's going to be the molar mass that we find on the periodic table. Now be careful, it's F2 in the formula. So it's going to be 19 times 2. That's 38.00 grams of F2 is a mole of F2. Again, the periodic table, we use the numbers as is always. There is no changing this fraction because of the problem. A molar mass does not get changed because the problem changed. The molar mass of fluorine will always be how we calculate it, period. So we're just going to do the rest of it. So now moles fluorine to moles of lithium fluoride. Again, that's my center. That's the chemical equation. So I'm going to look up here. 1 makes 2. So I'm going to put that there. Oh. 1 mole of F2 makes 2 moles of LiF. And then to turn it to grams, it's actually really nice that we did it once because we just copied the same number. 25.94 grams of LiF is a mole of LiF. And that's what you'll find with these more advanced stoichiometry problems. You tend to actually reuse numbers a lot. So it's actually less work than it looks because you're just copying down the numbers, but putting them maybe in a different order. But this will give us our answer. It ends up being 13.7 grams of LiF. So here is our second answer. Now, what do we take away? How do we answer the question? What is our answer? What is the maximum amount of lithium fluoride that can be produced from 10 grams of lithium and 10 grams of F2? Our answer would be
13.7.
It's, yeah, 13.7. This is the answer. We pick the smaller of the two. Again, this was important for our comparison purposes, but we ignore once question is answered. We don't need it anymore. So there's this tendency that like, I did all this work to get this number. What do I use it for? You don't have to use it for anything. It was just to make the comparison. But we always pick the smaller. We're limited to the smaller amount. And again, it's the bicycle analogy. We've run out of fluorine. We've run out of our F2 ingredient.
So you basically just, you did the same process, you just switched the initial starting substance.
Yeah. It's exactly the same. So you get two practices for the price of one. And then just to show it, again, the number line idea, we have a number line that represents the amount of lithium that I'm going to make. So if I used up all of my F2, I would make 13.7. If I used up all of my lithium, it would be 37 point something, 4. Again, the idea is that once I make, so if imagine myself moving along this number line, I'm making more, I'm making more, I'm making more product. But once I get here, I've reached the end of how much my F2 makes. So it's for this reason that we say the limiting reactant basically stops the reaction from continuing. And this is why we always pick the smaller number as our answer. So visually, this is why we do it. Alrighty. Yeah. I think this is a good place to stop. Right. So we've figured out what the amount of product we should make when we have given quantities of both reactants, or even if we had 3 reactants, we would just do the process 3 times and pick the smaller number. And then a good question, which will continue in the second half of this lecture, would be, well, if I use up all of my F2, that implies that I didn't use up all of my lithium. So what happened to the lithium? So we'll pick up figuring out, well, how much lithium is left over? And the answer is, if F2 is the limiting reactant, then lithium has to be left over at the end. So because it could have continued on. Much like, and then to just show the visual one more time, much like the bicycle idea, there is leftover frames. So when we define the limiting reactant, the excess reactant will have leftover. And we can use the same procedure, just with different sort of switched numbers, but the same procedure to figure out how much leftover we have. And that's sort of the teaser for next time. That is what we will do. But I think this is a good place to stop. This is kind of like a halfway point. So I'll go ahead and stop the recording.